Hello everyone. I'm Apoorva Shankar, Assistant Professor from the Department of Life Sciences, Kristu Jayanti College, Bangalore. Today, let us study about the scintillation counter. Scintillation counter is an instrument that is used for detecting and measuring ionizing radiation by using the excitation effect of the incident radiation on the scintillating material and detecting the resultant light impulses. The basic principle that is involved in scintillation counter is the radiation reacting with the scintillator, which produces a series of flashes of light of varying intensity when charged particle passes through them. The intensity of the flashes is proportional to the energy of the radiation. These counters are suited to measure the energy of gamma radiation and therefore can be used to identify the gamma emitting isotopes. The scintillation counter. There are three classes of phosphorus that is used for the scintillating material, scintillator. That is an inorganic crystal, organic crystal, plastic phosphorus. The light that is created in the scintillator strikes the photocathode of a photomultiplier tube, releasing at most one photoelectron per photon. So this is the image which you're seeing is how the basic working of the scintillation counter looks like. So the detecting materials, the scintillators consist of a transparent crystal, usually phosphor, plastic, organic liquid, that fluoresces when struck by the ionizing radiation. Cesium iodide in crystalline form is used as a scintillator for detection of protons and alpha particles. Sodium iodide containing small amounts of thallium is used as a scintillator for the detection of gamma waves, and zinc sulfide is used as a detector of alpha particles. Zinc sulfide is the material used to perform the scattering experiment. Lithium iodide is used in the neutron detectors. So these are some of the chemicals which are used in the scintillation counters for the detection. So what are the different types of components which make the scintillation counter? You have the photocathode, which converts the light photons into electrons. And then we have the dynode assembly, the series of electrodes. Dinodes are the series of electrodes which are used to amplify the signal. The dinodes are connected at intermittent voltage and typically about 50 to 100 voltage per step, the voltage increases and helps in the amplification of the electrons. Then we have the anode to collect all the electrons and generate an output. The voltage divider network helps in splitting the voltages that is required for the dynode, and the shell that prevents the component from the electric and magnetic field. So this is how the working of the scintillation counter is. So when we have a radioisotope that is emitting the gamma radiation, a high energy gamma radiation is emitted, and this high energy gamma radiation enters into the scintillator. So we can see that the scintillation counter has two important parts. One is the scintillator, and then we have the photomultiplier tube, and then it leads to the detector. Okay, so here in the scintillator is made up of certain materials which, when hit by the high energy gamma radiations, it gets excited, and when it is returning back to the lower energy state, they emit flashes of light. This is what the flashes of lights which are emitted in the scintillator counter. And these flashes of light enter into the photocathode. And this photocathode, which you see in red color, converts the photon energy into an electron energy. So now at this point, all the photons, that is the light, flashes of light which are emitted by the scintillating material, is converted into an electron by the photocathode. And these electrons are focused by using a focusing electron, which has a slit in between. And these electrons are called the primary electrons. And these primary electrons, after passing out through the focusing electrodes, are referred to as secondary electrons. And these secondary electrons hit the diodes. And these C-shaped things are called the diodes. And these diodes helps in the amplification of the electrons. So as you can see, firstly, the primary electrons are in the single beam when they are hitting the first diode. And then they are amplified and further multiplied. And at each step when they are hitting the diodes, the electrons are getting amplified and more number of electron beams are generated. And lastly, we have an anode. The anode is kept at the last to attract all the electrons which are emitted and amplified in the photomultiplier tube. And from this anode, the electrons are directed towards the detector. And the intensity of the anode, the electrons which are generated, is directly proportional to the intensity of the radioactive gamma rays which are emitted by the isotopes. So this is the simple working of the scintillation counter. So I will repeat this. So there is a scintillation counter which has the scintillating material, and then we have the photomultiplier tube. The photomultiplier tube consists a series of diodes. The diodes are used for amplifying the uh, electronic signal. So here we have the high energy photons, that is the gamma radiations which are emitted by the radioactive isotopes. And this gamma radiations uh, hit the scintillating material which is present in the scintillator. And this scintillators get excited, and when absorbing the high energy radiation, and when they are returning back to the lower energy state, they emit flashes of light. These flashes of light are collected by the photocathode tube and converted into the electrons. So at this point, the photons are converted into the electrons, and these electrons are directed by the focusing electrode towards the diode. And at every stage, the electrons hit the diodes. The electrons are getting amplified and they're getting multiplied. And these are called the secondary electrons. So as you can see in the image, the number of lines is increasing when it hits each diode. And finally, an anode is kept at the end in order to collect all the electrons which are generated. And these electrons are further detected by the detecting detectors. So this is in brief explaining the working of the scintillation counter. When the gamma ray interacts with the scintillation material, a visible light is emitted. This visible light interacts with the photocathode and electrons are emitted and attracted to the first positively charged diodes. When it strikes the diode, more electrons are emitted. The first diode is shaped so that it directs the emitted electrons to the next diode. The electrons are multiplied again by the second diode and sent to the third diode. And the electron multiplication continues throughout all the diodes in the photomultiplier tube. The result is a large flow of electrons striking the anode. Typically, each electron emitted from the photocathode will end up as about million electrons striking the anode. Afterward, the anode collected the electrons. A measurable electric current is generated, and the measuring device measures this current. The output of the scintillation detector is a pulse of electrons that is proportional to the energy of the original radiation that is interacting with the scintillation material. That is, the energy that is emitted by the radioisotopes are proportional to the impulse of the currents which are generated. So the advantages of scintillation counter: with the large size and highly transparent phosphor, it displays very high frequency. The impulse height is proportional to the energy dissipated in the phosphor by the incident radiation. Hence, it is possible to determine the energies of individual incoming particles. The time of the impulse being very short so that the resolving power is high. It can detect particles whose time of interval is separated considerably by less than 10 seconds. Because of very small dead time, the scintillation counter is capable for fast counting rate. It is more efficient for the ray counting with the larger scintillation or the scattered ray also counted it and gets an increased photo peak efficiency. The disadvantages are the poor energy resolution. In spots of its high detection efficiency, the recovering energy in the process of converting it into the light flashes and into photoelectrons, such detectors are capable of handling high counting rates in the spectroscopy work. The time of resolution is dependent on the spread in the transient time, and the spreading time is 2 to 5 nanoseconds. As the electrons are collected in the anode, we get negative impulse from the anode. The decay time of the anode impulse is around 20 nanoseconds to 50 nanoseconds. Hence, such detectors are capable of handling high counting rates in the nuclear spectroscopy work. That is about the scintillation counter. The applications. The scintillation counters are used to measure radiations in a variety of applications, including handheld radiation survey meters, personal environmental monitoring of radioactive contamination, medical imaging, radiometric assay, nuclear security, and nuclear plant safety. They're used to design for the freight terminals, border security ports, wage bridge applications, scrap metal yards, and contamination monitoring of nuclear waste. Several products have been introduced into the market utilizing the scintillation counters for detection of potentially dangerous gamma emitting materials during the transport. They are mounted on pickup trucks and helicopters for rapid response in the case of security situation due to the bombs or radioactive waste. Handed units are also commonly used. So this is more about the scintillation counter, the working of the scintillation counter, the advantages, the disadvantages, and the application. Hope the concepts are clear. Thank you.